Hello, welcome back to MATH152. Today I am going to use this opportunity to go over some of the common misconceptions and also common mistake that you made while you are solving questions involving improper integral. Unfortunately, we have to do it here because we are already running a little bit behind. So on Wednesday, we are going to go straight to chapter 11, section 11.1, where we're going to look at convergence of sequences and stuff. But the material on improper integral will be on the exam this Friday. So you better make sure that you know how to compute all these questions in your quiz. So we actually already seen all the solution here yesterday. I just want to stress that this integral, we can actually find this integral, the antiderivative. We can actually find the antiderivative not easily, but you can do it using u substitutions. So the u substitutions, usually also we don't really want to deal with u substitutions that involve square root like this. So if it's possible, like in this case, you can actually change this into u squared equal to x, and then you have 2u du equals to your dx. So this whole thing here will change to something that you know is computed using the integration by parts. So the antiderivative is possible to find. It's not super difficult to find this antiderivative. Some of you say it's impossible to find the antiderivative because you might confuse these questions with this particular questions. Now in this particular question, yes, the answer is yes, there is no antiderivative. If you are looking for a function such that the derivative of that function equals to e to the power of negative x squared, you cannot find this particular function here, so there's no antiderivative. But as you can see, for these questions, we can actually compute the antiderivative, and once we found it, we can apply the definitions and substituting the t and the 0 into the antiderivative here and compute the limit. Everything is pretty easy except this particular limit, which is of indeterminate form of infinity over infinity, so you will have to use the L'Hopital rule. But then once you see it, that it actually converges to 0, then you get the number 2. Now, there's also another thing that you have to pay attention to, which is the question asks if the integral converges, find its value. So if you think it converges, you do not want to use the direct comparison test, because when you do the direct comparison test, the only thing you can tell from the test is whether or not it converges or it diverges. And when it converges, you actually have no idea what values, what value it converges to. So if you think it converges and the question asks to find this value, this is the way to do it. So you have to find the antiderivative, substitute the value in, and you're getting answers. Now, some of you try to do a direct comparison test, and you say right away that x is greater or equals to square root of x. Now, this is not true, as you can see from this graph here. Your square root of x is actually bigger for your x value between 0 and 1. The y equal to x is only bigger than square root of x when it passes x equals greater or equal to 1. So if you really want to do direct comparison test, and you want to invoke this inequality, you cannot do it directly, so you have to split it into two parts. And here, all the x value here will be greater or equal to 1. Then this inequality will hold, and when this inequality hold, so you will be able to get this by multiplying negative across, and because exponential function is increasing, it's an increasing function. So once you have this, e of negative x will be really less than or equals to e of square root of x. So this is in the spirit of comparison test, because we wanted to find the improper integral involving these functions. If you don't really know how to integrate it, you might want to try to integrate something that is easier. So once we have this inequality, right here, so you can try to compute what this thing is by using the limits, the definitions, so you can see that it actually converges. Now, this is not a good news, because if you have inequality like this, and the smaller function here actually converges, we do not know what happens to this. So there's nothing really you can do unless you can find something that is bigger than this function and this function converges. Otherwise, the comparison test doesn't give you anything. It's not going to give you anything useful. And so because some of you actually know it, but you want to get answers, and you see that this is the only thing you can get, and a lot of you guys immediately claim that this actually diverges, then this diverges. No, this is not true. So please make sure that if you want to use comparison tests, you need to know when to use it. And you also need to know, like, if you do it this way, it actually wouldn't be able to help you to get the answers for the questions. All right, and also one hint is that the question really wants you to find the values, so the comparison test will not be able to do that even if you know the function converges, the improper integral converges, but you do not know what it converges to. Okay, so that's one thing. That's a comments that I want to make for problems 12a. And as also you can see that the question becomes way harder than usual because before this quiz, we were discussing the comparison test. So once you see this, you actually do not really know how to start. So should I use comparison test? Should I just use the definitions? So some of you get so confused because it's true, like now you have more tools. You do not really know which one will be the best tools to use. This is true in real life too, because once you have a question, you have like so many different ways to approach it. So these are kind of like the difficult question. The easy question will be the questions where you know exactly what to do. So like, for example, if you see this, you know exactly what you need to do. Okay, so, but things like this, you'll be like, should I use the definitions? Can I find the antiderivative? Should I use the comparison test? And so on and so forth. So questioning is going to be a little bit harder once you get to know a lot of tools. Okay, so the second part, which I want to talk about, is the second question here, part B. And for some reason, a lot of you thought that the problem actually happened at -2. Some of you thought the problem actually happened at 3. So because of that, I get a lot of answers, which is kind of looks like this. T goes to -2 from the left. And also a lot of you guys didn't mention whether you should approach the -2 from the right-hand side or from the left-hand side. So I get a lot of solutions that looks like this. So it's t and then 3, 1 over x to the power of 4 dx. Now, when x is equal to -2, it doesn't cause any problem with this function. This function does not have a discontinuity at -2 actually, but it have a discontinuity at 0. So the right thing to do, is to split them into 2 parts and then compute one of it separately. So this is what I want to say, because so the definition says that if you have discontinuity, so this is an improper integral of type 2. So the discontinuity happened at 0. So you split up the integral, the range of the integrations from -2 to 0, and then from 0 to 3. And then what happened next is that you have to investigate this separately. You look at this integral and see whether or not it converges or it diverges. So if it converges, that's good. Then you have to look at this function, this improper integral, and if it also converge, then and if you know the limits where it converges to, then the improper integral will converge to the sum of these two numbers. But one of it diverges, the whole thing will diverge. So one of it diverges, the whole thing will diverge. So if you look at the solution here, you see that I was investigating this part right here using the definitions, and I see that it diverges, and therefore this whole thing will diverge. Now, some of you did it this way, which is very dangerous. So this is the proper way of doing it. So some of you do it this way. So you split it into 2 parts, and then instead of investigating this thing and this thing separately, you actually put them together like this. So if you put them together like this, and when you find the entire derivative and you try to substitute this value in, these terms here, so these terms here that involve t, so these terms here and these terms here, okay, will cancel out. These two things here will cancel out always. So this is -1 over 3 multiplied 1 over t cubed, and this is positive 1 over 3 multiplied 1 over t cubed. So it will cancel out. So for a lot of you who did it this way, you will cancel these two out and you get the answers. I mean, if you split the things into tt like that, and when you do this substitutions, it will happen that this t terms will cancel out because the thing is that it will cancel out because this is from kind of like A to B and then F, and then you have from B to C and then F. This is A to C F. The reason why is because we can do it because exactly because they cancel out. So if you cancel out the t, there's nothing you can do, right? So you're not actually computing it like this. Let me remind you one more time. You split this into 2 parts, and then you investigate each of these integrals separately. So for example, here, as you can see, I was investigating what happens to the I1, which is diverged. So because of that, this thing diverged. The solution I gave it here is I'm investigating the I2, and then if I2 diverges, then I can say this thing diverges immediately. So you need to know you are not computing these two things at the same time. You actually have to break them into 2 parts and investigate each of this I1 and I2 separately. So look at this very carefully. And then we are either you are investigating I1 or you're investigating I2 separately, but do not do it at the same time. If you do it at the same time, the t terms here will cancel out. Then you will think that it converges. In fact, actually it diverges. Okay, so this is a comments that I want to make, which is a lot of you thought that something is wrong with the -2, something is wrong with the 3. Also, a lot of people miss that the problem is actually at 0. So please make sure that when you see something like that, you have to identify. You know that the range of integration is from -2 to 3, and you know that the functions that you try to integrate have a discontinuity at 0, okay? And because of 1 over x to the power 4, this thing is not going to behave well at 0. So you have to be extra careful on that. And the last problem here, okay, so the last problem here is part 3, which is the improper. This is an improper integral. You get a problem at x equal to 1. Because when you have x equal to 1, obviously you have square root of 0, and this is a big no-no. And so this is improper integral of type 2, actually. So the right way to do it is to recognize actually this function is integrable. I mean, we can find the antiderivative very easily. The antiderivative of 1 over square root of 1 minus x squared is your arc sine x, right? So integrating this dx will equal to this plus c. So we know that. So if you see that and you use the definition, it's very easy to see that it converges. Now, some of you want to try to do this by comparison test. As I mentioned in the part A, if you actually do the comparison test even correctly, you will not be able to find the values. You only be able to tell whether it converges or it diverges. But it's a good example to see how we actually apply the comparison test if you really want to. So suppose you don't know how to integrate this, which is not a good thing to do. I mean, like, you're supposed to know. But suppose you didn't want to integrate this, and instead you want to use comparison test. So what can you do with this? So a lot of you make an immediate mistake by saying that your x squared is greater than 1 minus x squared. I don't know why you say that, because you might think that this is positive, this is negative, and then so this is greater. I don't know how you thought of this, but this is actually not true. Because if you try to look at the graph of x squared, so x squared looks like this, and 1 minus x squared, so minus x squared looks like this, so this is minus x squared, and you shift up with 1 unit, right? So 1 minus x squared will look like this. So this is a y equal to x squared, and this is a y equals to 1 minus x squared, and you can see, so we are integrating between 0 and 1. So somehow there's a number here that we can identify. So if you try to solve for the common points here, if you try to solve the common point here, you can see that the common point here is 1 over square root of 2. Okay, so so this is a 1 right here. So part of it, so right here, for example, between 0 to 1 over square root of 2, this thing is not true. X squared is actually smaller. 1 minus x squared is actually bigger. So if you try to say that this is true, and therefore you have this, therefore you have this, therefore you have this, okay, let me say that one more time, so that so this is not true. So this is false. But if you continue, you will continue like that. You take square root on both sides, so you 1 over this thing. So now your inequality will flip, and so this is this, and then you have this, and then a lot of you say that because this diverge, which is true. Okay, it diverge for this this improper integral diverge, because the antiderivative is log x, and then when you take limits go to 0, it will just blow up. So it diverges. So because it's small, okay, and it diverges, therefore this diverges. That's how you use comparison test, but you use it, I mean, the way you use it is right, but the inequality that you use is wrong, so therefore this whole thing is actually wrong. The correct way of using comparison test is to do it like this. So if you look at, so for example, if you look at x squared and x, so between 0 and 1, you can see that x is actually bigger. Not x squared though. Don't think that x squared is always bigger, because it's power 2. This is power 1. But if you remember the number between 0 and 1, if you square this, you actually get a smaller number than 0.5, right? So so for between 0 and 1, actually x is bigger than x squared. So therefore you multiply negative, then you have this. So you add 1 on both sides, you have this. So this is true, and they are non-negative actually. So you take the square root on both sides, you have this. This is true. And so then you 1 over this, you will get this inequality flipped. So this is true. And so because you cannot really integrate this, you thought you cannot integrate this, but you know how to integrate this. So the integral of this is given by this. So this improper integral. So if you want to compute 0 to 1, 1 over square root of 1 minus x dx, so you use substitutions and you get the answer is actually 2. If you do it properly by taking limits on all that, you get 2. So therefore, this converges. So the bigger one converges. So the smaller one here, which also will also converge. So the right way to do direct comparison test is this. This thing converge, okay, and therefore this thing converge. So we know that. This integral converge, and that's the only thing we know. We know it converge. We know it converge and nothing else. If you look at all this work, the correct one though, not the wrong one here. So the correct one, if you look at this work, you will see that the only thing you know is it converges. That's the only thing you know. You don't know it converges to what value. In fact, if you use the definitions, you will know that it converges to pi over 2. So this is, I want to highlight the mistakes that you make for some of the students who try to do the comparison test. A lot of you actually do it this way. So unfortunately, the spirit is correct. The method is right, but unfortunately, it's based on a false premise. And it is a false premise, you can see, because the inequality is not right. So this is the difficulty of applying comparison tests, because you have to be very confident on your inequality. You really have to know which function is bigger than other functions, which one is smaller. So if you don't know that very clearly, do not use comparison tests, because you will get wrong conclusions, okay? And also try to recognize what are the functions that you know how to integrate. And this particular function here is really something that you should know how to integrate. And that's that. Hopefully by this you will have like one more example on how to do comparison test, which is here. You can really do the comparison test. If the question didn't really ask for the limits, it's just say, hey, if it converges, let me know it converges. If it diverges, let me know it diverges. Then this is perfectly fine. So this method here, this is perfectly fine. Saying this converge, imply this converge. This is perfectly fine. All right, I will see you tomorrow. And tomorrow we'll be looking at chapter 11, section 11.1 on sequences. All right, that's it. Bye.